In the last couple of videos, we talked about the Gram-Schmidt process. Let's use that on this matrix here. Let's call this matrix A. And we're going to use the Gram-Schmidt process to find an orthonormal basis for the column space. So the columns here, let's call them A1, A2, A3, and they span a subspace of R4, and we're going to find an orthonormal basis for that subspace. For reasons that will become clear a little bit later, instead of calling our orthonormal basis when we get it u1, u2, u3, we are going to call those vectors q1, q2, and q3. So that'll become pretty clear later on, or at least it's a standard thing that people do in this kind of a context. So first thing we need to do is turn a1 into a unit vector. We need the norm of a1, get a square root of 3 squared plus 4 squared plus 4 squared plus 3 squared. We can go ahead and pull out, well, we'll get a square root of 50. We'll pull out a 25, so we have a 5 square root 2. We take, okay, so we have q1 is a1 over that 5 square root 2, so 1 over 5 square root 2 times what a1 is. So that's our q1. Now we'll go ahead and use that to find q2. First we need to take the inner product of q1 with a2. We can pull out that 1 over 5 square root 2. We have 3 times 1 plus 4 times 1. Then we have a 0 there. Then we have negative 3 times negative 1. Here we get a 10, so 10 over 5 gives us a 2 on top, and 2 over square root 2, we can actually turn that into a single square root 2 on top. We find, this should be a2 minus our projection p. Remember, our projection p we get by multiplying this inner product by q1. So we have our a2, which is 1, 1, 0, negative 1, minus the square root 2 times the 1 over 5 square root 2 times 3, 4, negative 3. And when we work all that out, well, the square root 2's cancel out. That's very nice, but we still have the 5 on the bottom. And we're going to end up with a 2, 1, 4, negative 2. The norm of that, we'll still have the 1 over 5. We have a square root of all this stuff, or the square root of the sum of the squares of those. And that turns into well, actually what we get underneath here is 25. So you have square root of 25 over 5, we get a 1. So actually, we don't need to do anything. We divide the a2 minus p that we had up there by 1, and we get our q2. So one nice situation where we actually did get a unit vector. We don't expect that to happen, but in this case it did. Alright, now we need q3. So we're going to take the inner product of a3 with both q1 and q2. Go ahead and pull out that 1 over 5 square root 2. We have, what do we have? We have 3 times negative 1. We have 0, then we have 0, but then we have negative 3 times 1. So we get a negative 6 over 5 square root 2. Then q2, we pull out that 1/5. We have a 2 times negative 1. We have, again, a 0 and a 0. We have a 1 times negative 2. So we get a negative 4 over 5. Then we take A3 minus our projection. Remember, our projection is just going to be these two inner products times their corresponding Q's. So A3 was negative 1, 0, 0, 1. We subtract, or actually we add, because we have a minus sign here. We have 6 over 5 square root 2 times the 1 over 5 square root 2 that we have over there. And we have all this stuff. Then again, because we have the minus sign here, we subtract a negative, so we get a plus 4 over 5 times what we have here, so that we have a 1/5, 2, 1, 4, negative 2. We work all of that out. Nice fun little calculation there. We are going to get a 1 over 50, or wait, sorry, looking at the wrong spot in my notes. We have a 4 over 25, and then we have a negative 2, 4, 1, 2. So, nice small numbers, but we got a big number out here, but that's actually going to be taken care of when we find this norm. This square. We have a 4 over 25. We have a square root of 2 squared plus 4 squared plus 1 squared plus 2 squared. And kind of funnily, we have the same numbers here that we had under this square root, just in a different order. And so we get a square root of 25, so we end up with a 4 over 5. So once we actually divide what we have up here by 4 over 5, Q3 is going to be a 1 over 5 times negative 2, 4, 1, 2. So very similar to what we had for Q2. In fact, we moved some numbers around. All right. But these are orthonormal vectors that span our column space. And let's look at a matrix made up of these vectors. Actually, I'm going to go ahead and I'm just going to put a line there. I'm going to make a matrix capital Q, where my columns are going to be these three columns, these three column vectors. So I'm going to have to multiply through by the numbers out in front, unfortunately. So we're going to have here a 3 over 5 square root 2, 4 over 5 square root 2, negative 4 over 5 square root 2, and a negative 3 over 5 square root 2. There we go. Then our Q2 is 2 over 5, 1 over 5, 4 over 5, and negative 2 over 5. And our Q3 is negative 2 over 5, 4 over 5, 1 over 5, and 2 over 5. Okay, so we put them into a matrix because we started with a matrix, so we might as well. But why does that matter? I mean, we do have a matrix with all columns being orthonormal, and that's kind of nice to have. We talked about matrices that have that property in the last video, but really, how does that help us? Well, we're going to also make another matrix. We're going to call it R. This is going to be a matrix that's made up of some of the numbers that we used throughout this process. First of all, we're going to take all the norms that we calculated as our diagonal elements. So the norm of A1 is 5 square root 2. That's going to be the number we put here. The norm of A2 minus P, which was 1, we're going to put here. And then the norm of A3 minus P, this 4/5, we're going to put here. Okay. Next, we're going to take our inner products. So, first inner product that we dealt with was Q1A2, is the square root of 2. That is, we have a 1 here, and we have a 2 here. We're going to put that in the 1, 2 slot. So, the 1, 2 slot is right here. We're going to put the square root of 2 right there. Then we have two other inner products. We have 1, 3 and 2, 3. We're going to put that in the 1, 3 slot and the 2, 3 slot. So we're going to put those two numbers in there. So we have a negative 6 over 5 square root 2, and we have a negative 4 over 5. Now we don't really have anything else to put in these last 3 slots. We're just going to put zeros there. So what do we have here? Oops. We have a upper triangular matrix. So we have two matrices. We have one matrix whose special property is that it's orthonormal columns, and we have another matrix that's upper triangular and square. And it's actually non-singular because the diagonal elements are not 0. Remember, with upper triangular or lower triangular matrices, the determinant is the product of the diagonal elements. So if these are not all, if none of those are 0, then this is non-singular. It has an inverse. But the real amazing thing here, and it's not so much amazing if you actually work it out. It actually becomes relatively obvious in retrospect if you actually work out how these two are related. But it turns out that the matrix A is the product of Q and R. If you multiply these two together, you get the original matrix that we started with. We've essentially taken A and we've split it into two matrices with very specific and very useful properties. And so that's actually going to be very helpful. We're going to be able to use that fact in order to do a lot of things. And in fact, this ability to turn it into this is always going to happen when we actually start with the matrix with at least linear independent columns. If they weren't linear independent, then all this orthogonalization would have broken at some place, because because it kind of depends on you starting with independent vectors to begin with. But as long as we start with a matrix with independent columns, this will always work, and we can always get this kind of result. So we're going to call that breakdown of A into Q and R the Qr factorization. So if A is a matrix, an n by n matrix of rank n, remember, because A is n by n, it has n columns. All that's saying is that the n columns of A are independent. That also forces m to be at least as big as n. This won't work if we have fewer rows than we have columns. But as long as that's true, then A can always be turned into a product of Q and R, where Q is an m by n matrix with orthonormal column vectors, and R is upper triangular, and it's a square matrix with diagonal elements all positive. Actually, so we specified before that none of them were 0, but we can actually say here that they're all positive. And that's pretty obvious when you remember our diagonal elements were our norms, and our norms are always going to be positive numbers. That means that also that R is not singular. So we can actually always take the inverse of it. Now, I do want to make a note here, because this is a little non-standard maybe. Some people insist on having a different kind of Qr factorization. So we have a Q and R. I'm going to go ahead and put a little prime here to say these are not the same ones that we're working with here, but most people will just use Q and R for them. But the thing is that they will specify that Q is square, or Q prime is square, so that's actually an orthogonal matrix. So remember, an orthogonal matrix has to be a square matrix, but the main thing that we're really using here is that we have orthonormal column vectors. And then R prime, it's not going to be square anymore. It's going to be m by n, just to make sure the product actually comes out. Remember, Q prime would have to be m by n in this case, so R prime will have to be m by n. But it's going to be the R that we're talking about with a bunch of rows of zeros at the bottom. It's not really going to contain any more information than the R that we actually dealt with here. So it's kind of shifting some of the information from R into Q or something like that. And really, you can derive these two matrices the same way by using the Gram-Schmidt process. It's just for Q prime, you actually have to go a little bit further and find an entire basis for Rm and not just for the column space of A. That actually is a little bit more work than we did, and it really doesn't help us do some of the stuff that we're going to do in this section. There's some of the applications that we're going to have for this. So really, we're just going to stick with the definition the book gives us. It's actually easier to find, and it's enough to do all the stuff that we want to do with it. But just be aware that some people use a slightly different definition for the Qr factorization. Also, another thing to note here is we specify that A has to have rank n. That condition is really just so that R has non-zero diagonal elements. Any matrix can actually have a Qr factorization, as long as m is bigger than or equal to n. We can always find a Qr factorization. It's just that having rank n ensures that the R is non-singular, and that's actually kind of important for the applications we're going to use this for. So we're going to stick with that condition, and we're going to just stick with their definition for all this stuff. Okay, let's try our hand at a couple smaller examples. So smaller than the ones that we started with. I'm just going to start with. I'm just going to work on problem A. So this is from this section. So I put up both exercise 1 and 2 because really you have to do problem 1 for these problems in order to do problem 2, because you need to use Gram-Schmidt to find an orthonormal basis for the column space. But here our A1 is 1 or negative 1 1, our A2 is 3 5, and we're going to orthogonalize this. So first things first, we need the norm of A1. Actually, since I'm just going to be squaring that anyway, so let's leave out the minus. So we get a square root of 2. So our Q1 is just A1 divided by square root of 2. Then we go ahead and find A2 minus the projection. Or, well, our projection is going to involve our inner product. So let's find the inner product first. The inner product of Q1 with A2. We have that square root 1 over square root 2, but then we have negative 1 times 3 plus 1 times 5. So this becomes a 2. 2 over square root 2, well, that's just square root 2. We just rationalize it. So A2 minus that projection. So we have 3 5 minus the inner product times Q1. So 1 over square root 2, negative 1, 1. So when we those cancel each other out. So we have 3 5 minus negative 1 1. If we do that subtraction, 3 minus negative 1 is a 4. 5 minus 1 is a 4. When we take the norm of that, square root of 4 squared plus 4 squared. Really, we could have pulled out the 4, but we have a 4 square root 2. And so now, Q2 is just this 4 divided by 4 square root 2. The 4's cancel out. We have a 1 over square root 2 times 1, 1. Those are our vectors. So that's actually the solution to part A of problem 1. For part 2, for problem 2, which you would want to do at the same time as you did the problem 1, is you would go ahead and form Q from your results. So actually everything has a 1 over square root 2. I'm going to pull that out. So we're going to be left with a negative 1, 1 and a 1, 1. That's our Q. R is going to be made up of the things that we're actually working with. So first of all, this is going to be a 2 by 2 upper triangular, so that's going to be 0 there. Our diagonal elements are going to be our norms. Our first norm was a square root 2. Our second norm was a 4 square root 2. And then up here we're going to put our inner product. The 1, 2 that we dealt with is a square root 2. Or in other words, let's pull out that square root 2 and get a 1, 1, 0, 4. Okay, so this is an orthogonal matrix because since we started with a square matrix, everything here was the same square, and so we actually do get an honest to goodness orthogonal matrix. And here's our upper triangular matrix. It's as simple as that. Well, at least in the case where we only have to deal with 2 vectors at a time, at least. Obviously, the orthogonalization gets a little bit more complicated the more vectors that you have to deal with. But that's all you had to do here. Now, problem 5 is something that you're going to do on your homework. We're going to work on problem 6, but it's going to do exactly the same thing that you're going to do in problem 5. And we're going to work on parts A and B for now. We will address part C in a moment. So let's work on parts A and B. We're using Gram-Schmidt to find an orthonormal basis for the column space. Essentially what we would have done in problem 1, and then we're going to find the Qr Factorization, essentially what we just did into problem 2. So, very similar problem. Here A1 is 3, 4, 0. A2 is negative 1, 2, 2. Our norm of A1, square root of 3 squared plus 4 squared. Hopefully it's not too hard to see, that's a 5. So Q1 is a 1/5 times 3, 4, 0. Now we need to take our inner products. So Q1 inner product with A2. We have that 1/5 out in front, but then we have a 3 times negative 1 plus 4 times 2 plus 0. So we get 8 minus 3 is 5, so we actually get a 1 here. That's nice. We're going to take A2 minus our projection. So A2 is negative 1, 2, 2. Our projection is this inner product of 1 times Q1. So we have, just put in Q1 here. We get to actually work out what that is, and I guess we're going to have a 1/5 out in front. But then everything else turns into a negative 8, 6, 10. Or, I guess technically we could have pulled out a 2 as well. But the 2 is going to cancel out as we go. So, when we take the norm of this, we have a 1/5 times square root of 8 squared plus 6 squared plus 10 squared. Under here, we get, what do we get? We get, I guess we get 200 under there. But ultimately, what we get when we cancel everything out is a 2 square root 2. Because the 1/5 actually cancels out a lot of the, well, cancel out 25 from that 200. And that means that if we go ahead and divide these, we get a Q2 of, well, like I said, we could have factored out a 2, so that 2 is going to cancel a 2. We're still going to have the 5 on the bottom, so we'll have a 1 over 5 square root 2 times negative 4, 3, 5. Alright, so what do we have? We have Q is going to be these two columns. So our first column is 3/5, 4/5, 0. Our second column is negative 4 over 5 square root 2, 3 over 5 square root 2, and then, well, 5 over 5 square root 2, we can actually cancel those 5s, so get a 1 over square root 2. R is going to be a square matrix. It's going to consist of diagonal elements being our norms. So since we took two norms, you can see this is going to be a 2 by 2 matrix. Our first norm was a 5. Our second norm was a 2 square root 2. We have a 0 here, and then our last element is going to be this inner product, which is a 1. So again, if you multiply these out, you will see that you get the matrix, or this matrix A that we started with. We're not using B yet. We'll use that when we actually address part C. And since this is taking a while, I mean, this is a very calculationally heavy section here. A lot of the process in all of this stuff. I'm going to go ahead and cut this video here, and we'll actually go ahead and use this to solve some problems in the next video. So I'll leave that for a moment. You can probably see what we're going to be doing just from the problem you have on the screen. But I'll leave that for now. I'll see you in the next video.